Welcome to ECE 106 Lab 1. In this lab we'll be studying electric fields. Now electric fields are of course invisible, you can't see them. However, you can measure them using instruments. Now in this case we won't be using physical instruments, we'll be doing a simulation. We'll be using a software package called ECE, originally developed at the University of Colorado. It's one of a number of components that are used for teaching the physical sciences. Because the University of Colorado has made them freely available, they're used in a number of universities as part of their undergraduate curriculum. So let's get started with using ECE. Start by going to Learn, go to the ECE 106 page, you're going to go to Content, then go to Labs and Lab 1, and click on Charges and Fields. And there we have our interface. So you have this large empty working area, kind of like a lab table. You have a set of options at the top right, a set of tools below that, and at the bottom of the screen you have a number of charges and sensors you can place. All you do is take one of those charges and drag it onto the desktop. That's it. Now what you see here is a vector field. You probably heard that term before. And literally is a large number of vectors. Each of these arrows is a vector with a magnitude and direction. The direction of the arrow is the direction of the field at that point, and the brightness of the arrow indicates the strength or magnitude of the field. So, for example, this arrow is pointing away from the charge, as all the arrows are, and is fairly bright because it's quite close. The further away you go, the dimmer the arrows get. You're probably wondering why the arrows aren't centered on that charge I placed. Well, unlike the real world where you have a continuous vector field, here we have a finite number of vectors that we're using. And each of those vectors is evaluated at a particular point on a grid. We can actually turn on that grid so it's apparent what's going on. The electric field calculation is being done for each of these arrows at the center of one of these grid cells. If I simply take my point charge and drag it to the intersection of those grid cells, I get something that looks more or less correct. Again, these are all fairly approximate. We can add sensors to this vector field. There's a sensor. And with a sensor, that little yellow dot, we have again a vector, but in this case the length of the vector represents the strength of the field. So as I move the sensor around, the length of the vector changes. And I can have any number of sensors measuring the field at different points. Now I'm going to hide the field arrows so you can see this a little more clearly. We have a point charge of 1 nanocoulomb and a number of sensors. Let's look at the values of each of those sensors. I'm going to click on the Values checkbox, and now we see the field intensity in volts per meter at each sensor. Here, for example, it's 19.2. We also see an angle. That's really interesting. Obviously, an electric field in the real world is three-dimensional, but here we're looking at a two-dimensional representation. It works exactly the same, except we have the constraint that all the point charges and all the sensors have to lie in the same plane, the horizontal plane. So that angle we're seeing in degrees is the angle of the electric field relative to the positive x direction. And we're using a right-handed coordinate system, which means that as I move this sensor from here, where the angle is 0 degrees, and go counterclockwise, the angle increases. If I were to go the other direction, the angle would decrease. And in both cases, it reaches a maximum at 180 or minus 180. So that angle you're seeing is the angle of the electric field relative to the positive x direction. Now, in addition to having positive charges, we can add a negative charge. Notice how the directions of the vectors and also the magnitudes change as we add additional charges. Let's turn the electric field back on, and we can see that it starts to get pretty complex. Going to clear the entire display, reset it, and place just a couple of charges in. You can have a plus 1 nanocoulomb and a minus 1 nanocoulomb. Now let's just say I want to measure the distance between those two charges accurately. If you look at the right, you'll find a tape measure. And that tape measure, it might be hard to see this on video, has two orange plus signs, little crosshairs. I'm going to place one of them over the plus charge and drag the other one over to the minus charge. And it tells me the distance between those 2 points is 279.5 centimeters. And again, as I drag this meter around, this tape measure around, I can make these measurements anywhere I like. When I'm done, I can simply drag it back into my toolbox. So now that you know the basics of how to use a simulator, we're going to get into the lab itself. Now, the lab has a dozen questions in it, and we're not going to go through each of them individually. We're going to show you some of the basic techniques that you would use to answer the questions in the lab. Now, the first exercise is on electric dipoles. So we're going to start off with, again, a blank slate. We're going to turn on our grid, and we're going to pick an origin point. So let's just say we choose that as our origin. I'm just going to put a sensor there to mark that point. And we're going to add a +1 nanocoulomb charge. I'm going to try and put it more or less on a grid line. And now I'm going to add some additional sensors. I'm going to position them along the vertical axis above the origin I chose. I'm going to put 3 of them there, more or less equally spaced. And I'm also going to add one other additional sensor way far away from everything else. So, turning off the field for a moment, we see we have a positive charge and we have 5 sensors. 1 at the origin, 1, 2, 3, 4, and 5. So, we're going to turn on values and we're going to record the value in volts per meter at each of those 5 sensors. Now you notice there's not much of an arrow on this one because it's so far away and the field is very weak, therefore the arrow would be very short, it doesn't really show up. So we have a single charge and 5 readings. We're going to record those into a table. Then we're going to add a second point charge, and it's going to be the same distance away from the origin as the first one we had. So we have a positive charge here and a negative charge an equal distance from the origin. This is what we mean when we say an electric dipole. It has 2 poles, positive and negative. So now that you have a second point charge, you're going to record the values again. So you have 2 rows in your table, one with a single point charge and one with a dipole. And you're going to discuss how the field intensities at all 5 sensors change when you add the second charge. Spoiler alert, they do change, and not all of them change in the same direction. You're going to be asked to explain why. Now here's a hint. Remember, electric fields are vectors, and vectors have more than one component. That's the only hint I'm going to give you. The second question is, what is the direction of the electric field at each of the sensors? And why? You need to justify why it is the way it is. The next step will be to look at the 5th point, P5 up here in the corner. And you're going to measure the intensity of the field as you move the 2 point charges closer and further apart. So we're going to move that point charge in, and that one as well. You always want to keep them the same distance away from the origin. So you don't want to move one and not the other. You want to move them in pairs. And as you move them around, measure the intensity of the field at point P5 and keep track of it at each of those positions and plot a graph and find a best fit through it. You're then going to comment on how the field strength changes with the distance between the charges. The next step is to add additional positive or negative charges. So we're going to add another +1 nanocoulomb charge here and an additional negative 1 nanocoulomb charge there. And again, you're going to look at the value of the field at point P5 and comment on how it changes. For the second exercise, we want you to imagine you have a small test charge that you can place anywhere in the vector field. We want you to figure out where in the vector field the net force on that test charge is 0. Now obviously I can't show you examples because that would defeat the purpose of the exercise, make it far too easy. But you can show us by taking a screenshot of the vector field out of PhET and annotating it. You can do that however you like. You can bring it into a Paint program and annotate it there. You can print it out on a piece of paper, mark it with a felt marker, and scan it back in again. It's entirely up to you how you do it, but you need to show us where you feel that point is at zero force. You also need to justify it. Give us good, clear explanations for your reasoning. And that's it. That's all of Lab 1. If you have any questions or concerns, bring them up on Piazza, and the TAs and myself will do our best to address them. In the meantime, good luck, and I'll see you for Lab 2.